So first, I'm just going to tell a little bit of a story, I guess, about probability. So uh, probability is a very strange area of mathematics. Math has tons of different areas, calculus, um, linear algebra, geometry, uh, real numbers, abstract math, lots of different fields. One of them is probability. Um, and probability is something that somehow I think that in today's world, people just sort of have some kind of intuition for. When you talk about, oh yeah, 70% chance of rain, or um, demand is going to increase 50%, or whatever, there's this sort of gut level intuition of what that means. The but it's a fairly new area of math. So it wasn't until the 1700s that people actually tried to actually come up with any kind of math for probability. Um, and uh, yeah, it took, I mean, what, just a little bit before the founding of America, right? Like, I mean, that's less than 300 years ago. Um, that the math of probability was invented. Before that, it was just not very well defined. Um, there was this guy, Laplace, who's French, and he had a correspondence through writing letters. And what they were talking about was playing games. So, insofar as the way that people first started to try to frame probability was about betting. So they found like die that the Romans, Roman soldiers, they like to play dice and they would make bets, but there was no sense of making a prediction. You have die, you can roll it, and you get some random number. Random is another word that requires some definition, but in any case, you just throw die, they come up something, and you bet on whatever, I don't know, the two die are going to add up to. And uh, yeah, there was nobody who could game the system, who could be smart about the bets that they played. Um, None of this. So around the 1700s, Laplace and uh, sorry, I'm forgetting this guy's name. Laplace was writing letters to one of his friends, and they were talking about how to interpret this, and uh, that was sort of the first where the first equations of probability came from. And it wasn't until the 1930s that a guy from Russia named Kolmogorov wrote a like proper ground up. This is what probability is. He defined some axioms, and I will be going over these axioms probably a little bit later. They seem pretty simple and reasonable, but nobody did it before the 1930s. So everything that I'm teaching you about probability is kind of brand new. I mean, it's less than 100 years old. And any probability textbook that you pick up or anything that you read, these texts that I sent, all of them are after the 1930s. Feller, the first book that I sent, he wrote a different, I think, more easily accessible interpretation of probability. Um, Although Kolmogorov came up with the rules first, or how to do it, I guess. Um, So you might have learned probability before. If so, great. I'm going to be teaching it in a certain way that I think is accessible and correct, and the right way to think about some of this. So, there's my pen here. So I've got to turn off my cam so I can get to my screen. Okay. Again, this is not a probability class. I'm going to introduce to you probability in a way that is correct and but incomplete. So if you want a more formal treatment of it, you can refer to one of those two textbooks or really any standard textbook for more detail. So I'm going to define something called a probability space. I.e. sample space. So a probability space is two things. And just for some quick notation, if I'm writing it in parentheses, this means this is the term that I'm defining. After it comes the actual definition. I.e. means otherwise stated. So it's like AKA. This is the definition for probability space. Sometimes I might use the word sample space. They're the same thing, a probability space and a sample space. So this is a set and a function. I have some more notation here, but first I just want to talk about what a set is and what a function is. So define set. A collection of distinct objects. E.g., this is for example. Maybe I'll put this in. So e.g., for example, the set S of numbers. This is a set. Oh, and I'm denoting a set with curly braces. Okay, so when I'm using curly braces, I'm talking about a set. This set has size 3. It has 3 elements. And okay, so that's one example of a set. Here is another example of a set. What's this one? This two. This is also a set. So there's still, this is also has size 3. It also has 3 elements. These elements are names. So when I say object here, an object can be anything you want. They can be numbers, they can be names, they can be smiley faces, they can be groups, anything you want. Um, you put it together and it you can refer to it as a set. One quick note. Should make this a 2 just to, okay. Uh, these two sets are equal, okay? Repeats do not count in sets. I mean, you can technically write a set like that, but this is not considered two different objects. This is considered one object because it's the same object, it's just repeated. So you can always simplify sets of this kind and write them more simply with no repeats. Okay, so that is a set. A function. Is a mapping of elements in one set to another. Notation. Let's see. This is an example of a function. And just so for notation, this is the domain, and this is the range. That is the symbol for a mapping. So here it takes a set of 7 things and outputs a number. So there's another e.g., I guess, an embedded e.g., e.g. f of Monday equals 70. So this could be a function that says the probability of rain as a percentage. Okay, so the probability that it's going to rain on Monday is 70%. Every day of the week, I can assign some probability of rain between 0 and 100. So that is an example of a function. And this is the way that I'll be writing functions. This is the name of the function. Then a colon, so I'm giving it a name. And the colon is saying, is defined as, and then the domain mapped to some range. This is the way I'm going to be writing a function. Any questions about either of these, a set or a function, or what they mean? And if no, please write no. No. Okay. Then a probability space is two things, a set and a function. The set I am going to write as this. Pronounced omega. Okay, so when I write omega, this just means the world, the set of events in the world. And even though it looks like a funny symbol, just think of it as some kind of set. It has some size and whatever. Oh, one other thing. Give another example. Real numbers are a set. And so, well, let me do integers. Easier to write. This dot 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 means infinity. So, or means it just continues in this way. So here, that's a z. The set of integers. So 0, 1, 2, 3, 4, 5, all the way up to infinity, and also including negative numbers, whole numbers, up to infinity. This is also a set. This set has size infinity. Okay. So this is just some set. If you can count the elements, that's a finite set. This is going to be for finite probability distributions. And this is the only thing we'll talk about today and next class, is when things are finite. This, when you have something that, a set that is infinite in size, then this is called continuous, and continuous distributions. This we will come back to maybe next week, maybe the following week. So for the rest of today, actually for this week, just think of probabilities as being a set of things that you can count. And there is also a function, f, that puts this between 0 and 1. So again, think of this for now as being finite. Maybe it has 10 things in it, or 6, or 100, but you can give some number to the size of the thing. And then a function that takes elements of that set and gives them a value between 0 and 1. So this is very similar to this, except instead of 0 to 100, here I would say it's a 0.7 probability of raining on Monday instead of a 70% chance. I'll just divide everything by 100, and this is exactly a probability function. So every single day should have a probability of rain, and each of these probabilities are going to be something between, for up here, between 0 and 1. Okay? And this is what probability is, and I'll say it many times. Probability, so a probability space is two things. I'll even do this. There's two things in a probability space. There's a set and a function that maps that set to this range. Values between 0 and 1. If I say that there's a minus 10% chance it will rain, that's nonsensical. So negative numbers aren't allowed. If I say that there's a 200% chance of rain, that's also nonsensical. If it's a 100% chance, it means that it's certain. You can't go above 100. So scaling those, you're stuck between the numbers 0 and 1. And if you have these two things, you have a probability space. So uh, oh, because I've already said this down here, that this thing is how I'm going to be naming the function. Just to make things a little bit easier, I'm going to name this function PR for probability. I mean, I could put whatever I want. I could keep it F or whatever. But this way, I can write PR stuff, and it's more easily read as, oh, the probability of the thing inside happening. Okay. Let's see. So we have some probability space omega, and this is a space that have some finite number of things inside of it. Let's call it the faces of a die. Face 1, face 2, face 3, face 4, face 5, and face 6. I'll say this is the outcomes of a die roll. You could also write this in set notation as face 1, face 2, and continue on until you stop at face 6. So writing it in this more graphical way and writing it in this squirrely bracket way, it's the same thing. You can choose whichever form you like to think about it in. So this is a set, and this is a set of all things. Everything that can happen must be inside of this set, omega. Now, an event is a subset of omega. For example, oh, this red epsilon. So I'll use this sort of E looking character, a curvy E, to represent an event. It's pronounced epsilon. I hope these things aren't confusing. It's just I'm used to it, so I'm trying to introduce it slowly, so I don't lose you somewhere. But an example event could be epsilon equal to the die is even, and written in set notation, I'll give you your first chance. What should I put here? How would I write this event as a set? The die is even. I'll give you a minute. Excellent. Great. Yep. Some of those work. Just to, yeah. Phase 2, phase 4, phase 6. So this is a set of 3 things. Each of these 3 things appear in the world. I could not write phase 7 here. This can't work because this is not an event of this world. This world has 6 possible things. And so the event has to be some collection of them. You can take or leave as many as you want, but everything has to come from inside of this circle. Notation. E epsilon omega. This means is a subset of. Okay, so events are a subset of the probability space, or of the set omega. The probability space also includes a function. This is not talking about that yet. So you might see this or this. It looks like a C, but this is a subset. This is a proper subset. Let me keep these green for notation. Do this. Whatever. Okay. Think of this like this is less than or less than equal. It's the same type of thing. So if epsilon is just a subset of omega, it can include everything. So maybe epsilon equals omega. This would be epsilon equals omega. But it doesn't have to include everything, but it can. So this is okay here. But if you're using this symbol, you can't include everything. It's like it's strictly less than. If x is less than 5, it cannot be equal to 5. Anything under 5 is okay. So for sets, instead of this angle bracket, they use this softer thing that looks like a C. So here, this would be okay. Or actually, let me do this one different color. So this is okay. That's okay. This is still a proper subset. This is still a proper subset, still a proper subset, still a proper subset, but now it's maxed out. It can't take anything else in. Okay, so just as far as notation goes, that's the difference between these two. Any questions about that? No. Okay. So that is what I will mean by an event. So when I talk about probability, I must have a probability space that I'm talking about. If somebody talks about the probability of something happening, it doesn't mean anything unless they give you what the probability space is. What's the set of possible outcomes? And every single one of these outcomes has to have some probability of occurring. Um, and so you can't just talk about the probability of rain by itself. Like behind it, what like there's things that you're not saying that um, the probability space here is it's either going to rain or not rain. It's not I'm going to eat French fries. Like that's not included in that space. The space that you're talking about is rain or not rain. Oftentimes it's understood, but um, yeah, uh, it's important to know what you're talking about when you say the probability of something happening or not. um, oh, okay. More terminology, notation, terminology. These are called elementary events. Sorry. Huh. So um, each of these points are an elementary event. It's just a single point. That's what an elementary event is, or it's a single item in the set, just a single one. Events can take many elementary events and package them together in a set, and that is an event. So elementary events are just one dot. Events can be many dots. um, Now, uh, yeah, part of what we're going to be doing over the next couple of days are taking statements that people say and just making them formal, um, putting them into this sort of uh, formal framework. And again, this formal framework is fairly new. I mean, like less than 100 years. There were ideas about how probability worked. Um, in some ways, like in the 1700s, but yeah, before that, nothing. So all of this is just trying to introduce you to um, what the rules of probability are. And uh, when you make statements or when you hear statements about the probability of something happening, how to correctly interpret it and not misunderstand somebody, or that somebody else might misunderstand exactly what they're saying. Um, so here, I'll still talk about an event. Um, and I'll continue. Um, Okay. So an event is a set. In particular, it's a subset, and it's a subset of the world that is in the probability space that you're talking about. In this example, we're talking about rolling a die and what the outcomes could be of rolling a die. I'm only considering 6 possibilities, no crazy stuff where the die is laying on its side or its edge or anything like that. The die is going to land flat and it will read one of 6 numbers. That's the world. Those are all of the possible outcomes that I'm considering. And here, I'm defining an event of the die coming up even. So this is a subset of the world where any outcome is some even number. And I've captured all of the even numbers. So the die is even. That's this event. So let me ask you, what is the probability of epsilon? Epsilon here is the die is even. That's how I'm defining epsilon. So what's the probability that the die is even? .5 is 3/6. Yeah, good. Okay. All about the same thing. So you are partially correct. If you want to talk about the probability of something, you need 2 things. The set and also the function, the probability mapping. Here, so far, I've given you the set here, but I haven't told you what PR is. What's the mapping? So what's the probability of face 1? The probability of face 2, and on. This I never gave you. And so all of you had this assumption that I was talking about a fair die. Might not be fair. I mean, maybe it's a weighted die, because I like to cheat when I play games. So I'm going to weight my die and screw up your math. So in any case, I'll stick to the fair die here. To be complete, each of these, we'll say it's a fair die. And so each of these have a 1/6 probability of occurring, any single face. So given this now, the probability of epsilon is equal to the probability of all of its elementary events added together. It's 2 plus probability face 4 plus probability face 6. And so this equals 1/6 plus 1/6 plus 1/6, which equals 3/6, which equals 1/2, or 0.5, or whatever you want. Okay. So here, the probability on a fair die of rolling an even number is 1/2. But this 1/2 isn't just 1/2. I mean, 1/2 can be many, many things. 1/2 can be 5/10. 1/2 can be 100/200. this 1/2, this one here, is not this 5. It's not that half. It's not this half. This half is 3/6. That's what this half means. Not 5/10, not 100/200. This half here, the probability of rolling an even number on a fair die is 3/6. That 1/2. And this 3/6 isn't just any 3/6. I mean, I can, this 3/6 is in particular the addition of these 1/6. And these 1/6 are each of the individual probabilities. Okay, so I know you have all of these assumptions in your head, and I can ask a question and you can throw out like, oh, it's a half, of course, 3/6, whatever. But there's a lot of assumptions and quick calculations you're doing in your mind. So part of something to try to get used to for the next class or two is to slow down and to try to break down when you give this answer what's happening. Like it's a gut feeling oftentimes, but there's a process that you're following. Later, I will give plenty of examples where your intuition will fail you horribly. Like there's a lot of things about probability that you feel like it's one way, but it's really not. And you can prove it going through these types of steps. And you feel about it another way. It seems it's an uncomfortable thing to know just how bad your intuition is at times. Now I'm asking kind of obvious things, or things that occur to you really quickly and your intuition is correct. But yeah, there's a process to justify your intuition. Okay, so again, a probability space is a set, it's a collection of objects and a mapping of these objects to some numbers. An event is a subset of the set in the probability space. And the probability of an event is equal to the probability of everything it's comprised of. So this event here is defined by these 3 elementary events. And so the probability of this event is the probability of getting face 2 plus the probability of getting face 4 plus the probability of getting face 6, which in this case is a half. Okay, any questions about this? No, okay. Any questions about the course? Like especially this latter part of it tends to be the way that I teach. Is it too formal? Am I using too many colors? Yeah, I don't know, any kind of feedback. Are you gonna post these notes on Blackboard? Sure. Yeah, I can make them a PDF and put them on Blackboard. Okay, good. So far, so good. It might seem really boring and tedious in the beginning. I'm not sure, honestly, because I can't see your faces and stuff. But I wanted to. I'm teaching everything, so it's all contained. You don't need any other outside resources. Of course, any outside resources you want to use, YouTube videos or books or blogs or whatever, go for it. And yeah, so right now we're just talking about the basics of probability. We will continue with this on Thursday. And oh, wait, let me see here. Um, actually, we still have some more time. 3:40 this class goes to. Jeez. Okay. It's okay. Um, let's take another break then. We'll take another 10-minute break and I can cover maybe one more thing and then we'll call it a class. Okay. So let's take like a 10-minute break and yeah, I'll teach just one more thing. Okay. So we're talking about probability. And when people make statements like the probability of so and so happening, the chance of something happening, the likelihood of something, there's the way that people speak, and oftentimes they're either correct or very close to being correct, but um, for in more formal settings, like there's a there's an arena that the person is coming from when they're talking about the probability of things happening. There's lots of assumptions, there's lots of things that a well informed person will include when they're making the prediction about something happening. That's sort of the motivation behind probability is trying to think about the future. You're trying to make predictions. If it's already happened, then there's no sense in thinking about probability because it's already happened. This is concerned about what the future is going to bring and trying to make predictions. Sometimes you can make very informed predictions. And that is what we're building up to when you want to understand everything that's in this arena and to have all the pieces in the right place to build on top of. It's pretty easy. You just have to be vigilant and careful. So, formally, a probability space, also called a sample space. Also, I'll add this. I'm gonna do another IE. Otherwise, a formal statistical model. Okay. So part of this is just demystifying vocabulary. Probability is built on top of a probability space. People will refer to this in different ways. Sometimes they'll use the word sample space. Sometimes they'll talk about a formal statistical model. So this is the formal statistical model that I'm working from and it predicts whatever. All of it is two things. There's a set of events and some function that maps elements of that set to the numbers between 0 and 1. That's what a probability space is. There's a couple more rules, I'll get to them, but that's basically it. All the other rules are super obvious. Okay, so when you're talking about a probability space, I'll also refer to this as quote unquote the world. This is what I mean by that is whatever the context is. So if you're talking about the probability of rain on a particular day of the week, then I know that you're talking about days and you're mapping them to some numbers, and one of those days will have a higher probability of rain. Uh, yeah, so I might accidentally or sometimes intentionally use different sayings for these things, but a probability space, formal statistical model, sample space are all referring to just these two things. And this is the world. This is what you're talking about. If you're talking about rolling a die, then your world is going to have 6 things in it. If you're talking about flipping a coin, your world is going to have 2 things in it. If you're talking about the day of the week that something is going to happen, your world is going to have 7 things in it. Whatever. And so that's when I say the world, that's what I mean. It's the context of all the possible outcomes of whatever. An event is a subset of the world. The world has many individual events that can happen. An event is some collection of those possible outcomes. It could be 1, it could be 0, it could be many, or all. Okay. The probability of an event is defined. I should give this a definition. The probability of an event is the sum of the probabilities of its elementary events. This is a definition. Sometimes there's lemmas, theorems, in which case you can define things how you want. Not the case in definitions. A definition you can't argue with. It's just the way you're defining it. You can't change it. There's no reason to change it. Because I want to, I'm making a definition, and I'm defining the probability of an event as being the sum of the probabilities of the parts that make it up. Okay. Okay. Now, I want to try to emphasize so far what I'm trying to do is to give an arena to play in, introducing the rules of the game. And if I have not introduced a rule yet, it does not exist. Okay, so only what I've said so far, those are the things that you can use to try to answer questions. Anything outside of that doesn't exist. So imagine yourself being in a very small box that's confined, and the only rules are the ones that you've heard so far. Probability spaces are a set, collection of things. You have a function that maps every single element of that set to some number between 0 and 1. And events are a subset of these individual events. Okay? So just prefacing stuff. Okay. Oh. Let me make a remark. Okay. So A probability space describes exactly one realization of the experiment. Here, when I use the word experiment, I might use the word experiment. I might use the word sample. Um, what I mean is that we have a set of things and a function that maps them. And if I conduct an experiment, or otherwise I take a sample, what I mean is that one time I pick out um, one of the elementary events according to each of their own individual probabilities. So here, the outcomes of a die roll. This probability space are these two things. There's the space, these 6 outcomes, and then there's the probability of them happening. Every single one has a probability, um, and yeah, all of them add up to 1, and these things will come later. But uh, so when I run an experiment, that's throwing the die one time. That's it. That's what this captures, this world. And then this is the probability of if I throw the die one time, out of the 6 possible things that can happen, um, how many, what's the number between 0 and 1 that I can expect that outcome to occur? So that's a probability space, one realization of the experiment. So here is question. Okay. Any thoughts? So we have this probability space, and we want to know um, if we can answer this question, and if so, how. And if you think you have a thought, can you please unmute yourself? Or if you have no idea, you can type no idea. Hello? Are people still in the class? No idea. Okay.
Is it 136th?
Okay. Why do you say 136th?
Because it's a 1/6 chance for the first outcome to be phase 1, and then you multiply it by the 1/6 chance for the second outcome to be phase 2.
Okay. Great. Thank you. Anybody concur with Mateo, or do you agree? Do you disagree? Hmm. Okay. So, uh, it's a good intuition, but it's not quite right. I tried to preface it by saying that we're in a very small box. Um, and so this, no, no. Omega describes one diroll. So what we have in our world is a single diroll. That's it. Um, these it how like there's no way to each one of these. This world has 6 things inside of it, and among those 6 things is not face one, face two together. I mean, there is a face one and there's a face two, but these are 2 separate, distinct things. Um, this set, okay, so we need to define a new set. We need to define a new world. I'll call it squared. So we're going to do this thing. If omega does it once, then here we can do it 2 times. So this is going to be another, collection of whatever events that we can also represent as a set of possible outcomes. Can anybody say what the set of outcomes would be for this experiment? Rolling the die 2 times. What's an example of a possible outcome of this? If nobody unmutes, I'm just going to choose somebody at random.
Would it be something like 1, 3?
1, 3. Sure. 1, 3. Yeah. The way that I'll write this, I'm going to stick with the faces. Face 1. I'll write this here. So one possibility would be face 1, face 3. And to emphasize that this is a single event, I'm going to put it in parentheses. So this face 1, face 3 in parentheses is a single point. Maybe this one. That one point is face 1, face 3. Okay. How many points do I have in here? Oh, you can't see anything I'm writing. Really? Let's see. I'm sharing it. Here, let me try this quickly. Okay, so I'm going to do a quick poll for how many people can see my screen. Okay, so nobody can see my screen. Weird. Okay, let me try unsharing and resharing. Okay, that's fine. I'll stop sharing some of this and try that. Okay, how is that? Any better? Okay. Great. Thank you for letting me know. Great. So this and go back up here. Okay, so we're talking about this question. Can we measure the probability when a die is rolled 2 times? Maybe the first outcome is face 1 and the second outcome is face 2. So right now we're trying to define this world. A single die roll is omega, so I'm calling 2 die rolls omega squared. Here I'm representing that as sort of a circle with points inside of it. You can also write it in this sort of set notation. Vincent said that face 1, face 3, that is one event that can happen in this world. And so the squiggly brackets here, these represent a set. But this face 1, face 3, I'm putting in parentheses to indicate that that's one element of this set. So this is going to have other elements, but this is one of them. And pictorially, this face 1, face 3 is just one single point, maybe this point. So this one point corresponds to this one event. The event that in the world where you throw a die 2 times, the event on the first roll and the event on the second roll. Okay, so my question is, sorry, I keep jittering. My question is, this set, how many elements does it have? How many possible outcomes are there for rolling a die 2 times? "36." Right. Yes, exactly. So here, those 36 will be the event face 1, and going on for a while and ending in face 6, and stuff in between. So here, notation. This means size, or the cardinality, really. Size or cardinality is 36 in this case. So if I write these vertical bars, that just means count up the number of dots, or count how many elements are in the set. It's written this way. Great. Okay, now, is this a probability space? Okay, Vincent says he thinks so. How about others? I don't know is also an acceptable answer, but please type it. Or unmute yourself and say. I have 1 out of 13, 2, 3 out of 13 responses, 4. And I'm not sure, yes. Not sure. Not sure. Okay. Um, so I'll say it again and probably a few more times. A probability space is two things. Go back up here to the top. Probability space. Two things. You have a set and a function. These two things define a probability space. In the same way that rolling a single die, this was not a probability space until we defined this function. This has the same problem. Here we have a set. These are, it's a set of events that could possibly happen in the world of throwing a die 2 times. These are all of the possible outcomes of that. But are we throwing a weighted die? Are we throwing the same die 2 times? If we're throwing a weighted die, then it's going to really screw up the probability calculations. So this is 1, and then 2, you need the probability function. And so this needs to map every element of omega squared to a number between 0 and 1. To make things easy, we'll say that it is a fair die. So the probability of this, of the event, rolling a face 1 2 times is 1/36th, and the probability of throwing any actually is going to be 1/36th. 1/36. Okay, now this is a probability space. We have our set and we have our function, and we know that we're dealing with a fair die. I can't talk about the probability of rolling a 1/1 if I don't know which die you're throwing. Are you throwing a weighted die or a fair die? And whichever one you tell me, then I can make solid predictions about which faces I'll see more often than others. Okay, so I'll repeat it again and again. A probability space is two things. It's a set and a function. You need both. Okay, now this squared is this. Oh no, note. Equals omega times omega. This times is set multiplication. So the same symbols are used in different areas of math for different things. Here, just to save writing space, omega, I'll say it's 1, 2, I'll cut out the face writing. 1, 2, 3, 4, 5, 6. So this is omega times omega. 1, 2, 3, 4, 5, 6. So what does this equal when you multiply these together? We've already kind of answered it, but I'd like anybody to put it in their own words. Okay, how about Brian? Are you there? Do you have can you unmute your mic?
Um, would it just be like all 36 possibilities?
Yeah. Yeah, exactly. Okay. So if these are all 36 possibilities, like how do you get to 36? Like why 36?
Well, you could like it's 1 1, and then the next one would be like 1 2, 1 3, 1 4, 1 5, 1 6.
1 3, 1 4. Okay. Right. 1 4, 1 5, 1 6, and then what?
And then you would go like 2 1, 2 2, 2 3, 2 4, 2 5, 2 6.
Okay, great. So I'll just keep that going to 6 6. Here, let's take this one and this one. 1 2 and 2 1. What's the difference between those?
Well, in 1 2, the first time you roll the die, you get 1, and the second time you roll it, you get 2. And in 2 1, the first time you roll the die, you get 2, and the second time you roll it, you get 1.
Great. Perfect. Yeah. Thanks. Yep, that's it. So, in set multiplication, the way that set multiplication works is you find all possible pairs. So here, what Brian was saying is this here, this collection, and this is 6 out of the 36, and I'm going to have 6 collections of 6. Whatever. Yeah, I'll have yeah, multiple collections of 6. 6. Okay, great. That this first set of 6 is this first one, and you match it with every one here. So 1 1, 1 2, 1 3, 1 4, 1 5, and 1 6. And for these, the 2s, these you're going to match the 2 up with every single one of these. And so you take the element, the first element in the first set, and you match it with every element in the second set. That's called a pair. And so these are all of the possible pairings of the first one with elements in set 2. And then you do the same thing with the 2, and you pair 2 with everybody that's here. And then you take 3, and you pair 3 with everybody, and then that will be here. And you do that for each of them, and you end up with 36. Okay? So, in general, the set product, i.e. the cross product. So, given sets omega 1, omega 2, omega I, if this is equal to E1, E2, whatever, E, J, E prime 1, E prime 2, E prime K. So this prime is saying that this event, this E prime 1 event might be different than this E1 event. And also the lengths of the worlds might be different. So omega 1 might only have 10 elements, but in general, omega 2, it might have 100. Yeah. And this equals, I don't know, EI is 2, instead of using primes. EI1, EI2, L. So if you're doing this, if you're multiplying many, many sets together, then the elements of them will be E1, E2, up to EI, of matching all of the first ones and going all the way to the end ones, J, E, K, L. Okay. And we'll call this omega star. It's a big omega. Then the size of omega star, well, maybe I'll ask that to you guys. Yeah, so this is the general kind of rule. If you know the way that this works, you're set. You have two different worlds, two different sets, and when you multiply them together, you get all pairings. In the case of rolling 2 die, you match the first element up with all the others in the second set, then you take the second element in the first set, find all possible pairings in the second set, and you end up with like 36 pairings. Even though this has a size of 6 and this has a size of 6, the size of the resulting set is 36. It's a much bigger number. So here, in general, if you have many different events, I roll the die one time, and then I roll the die a second time, and then I roll it a third time and a fourth time. Maybe I roll the die 10 times. So then I would be equal to 10. And the first of these events would be maybe I roll a 1 every single of the 10 times. So 1, 1, 1, 1, 1, 1, 1. 10 of them. And all possible combinations of stuff until I roll all 6s, like 10 times in a row. Just 6, 6, 6, 6, 6, 6. And everything in between would be this set. It's a very, very big set. So the size of this is equal to the size of each of them multiplied by each other. The reason is the same reason as above here when you're thinking about die. So you roll a die one time, you have 6 possibilities. If you roll a die 2 times, you have 36 possibilities. You take the size here, 6 possible things that could happen, and for all 6 of these, I'm considering their pairing with all possible 6 things in the second set. So you have 6 times 6 is the size of this set. So in general, that's the way it works. Yeah. So let me question. If I roll a fair, no, it doesn't matter if it's fair or not. If I roll a die 10 times, how many possible outcomes are there? I.e. omega 10. What's the size of omega 10? So you roll a die once, you have 6 possibilities. You roll it twice, you have 36 possibilities. Now I want you to roll the die 10 times. How many different possibilities are there? How many possible outcomes are there? I'll give you a minute. Great. Yes, I'm seeing 6 to the 10. Correct. Valentines. Is that what 6 to the 10th is? It looks, yeah, that looks about right. Looks like it's, yeah, great. Thank you for calculating that for us. So, correct. This is 6 raised to the 10th power. For the first possibility, for the first roll, we have 6 outcomes that are possible. If you pair all of these 6 outcomes with 6 possible pairs, then you have 36 pairs. For each of those 36 pairs, you then have another 6 things to make the triplets. So 1, 1 can be matched up with the third die roll of 1 or 2 or 3 or 4 or 5 or 6. So that's 6 possibilities, but 1, 2 has the same, 1, 3, and on and on. And you have 10 of them. Great. Okay. Now, here's another question. The probability of, call it 1, 1, whatever. Yeah, what's the probability of rolling 2 1s in a row? And why? We're playing by, let's see. Yeah, call it a fair die. First, let's call it a fair die. For fair die. And when I say a fair die, this is saying 2 things very concisely. First of all, omega is 1, 1 up to 1 or 6, 6, 2 times. Yeah, actually, yeah. So it's understood that I'm rolling the same die 2 times. So when I say that it's a fair die, first of all, it's a die, but also the probability of each of these are equal. Let's do it this way, actually. All the probabilities equal each other. So what's the probability of rolling 2 1s? Don't overthink it. 1/36. Great. 1/36. Excellent. And what is this 1/36? How are you getting 1/36? Great. That's right. This isn't 2/36 minus 1/36. That's also 1/36, but that's not the one we're talking about. The 1/36 we're talking about is 1/6 times 1/6. So given a probability space, if you have a sequence, for example, of events, then you can take, for each world that the event happens in the sequence it happens in, and you can first construct the list of possible outcomes. But this is yet to be a probability space, because a probability space also needs a probability function. So set product. I'll do this. Define. I'll call it a probability product. Very similar to a set product. So this is what we've already talked about. The probability product, you take two sets or whatever the sets are that you're dealing with, and you come up with the set product. But the probability of, in this case, E1, E prime 1. So E1 is coming from the first thing happening, and E prime 1 is coming from the first possible outcome and the second thing happening. This is equal to the probability of E1 times the probability of E2. I won't use the cross here. I'll use the dot. Oh, shoot. Yeah, sorry, I'm getting more notation. So I'm not writing this generally, okay? Up here, I wrote it generally. It's exhausting. This is a little too formal. So I'll just stick with getting the point across here. If you have two probability spaces and you want to know what happens with one event following another, then assuming that it's the same type of event, like rolling a die, then the set of possible outcomes are all pairings of outcomes from the first roll die, or the outcome of the first roll die, and the outcome of the second die roll. And the probability is the product of the probabilities. So the probability of the first event followed by the second event happening is the probability of the first event multiplied times the probability of the second event in the second world. Here, this probability, I'm writing the subscript here to just let you know which world it is that I'm talking about. So this probability function is different. This is different than these two. So not the same as these. This probability is a function that maps 36 things to 36 outcomes. This one. So if this is the set, then the probability, we'd have the probability of rolling 2 1s all the way to the probability of rolling 2 6s. And so each of these are 1/36. So this probability function has 36 different entries. This one has 36. This probability function only has 6 entries because this is for a single die roll. Okay, so to avoid confusion, I will write as a subscript to the probability function the set that it's mapping. Okay. Yeah, I don't know that I want to go much deeper than this now. Yeah, maybe I'll just leave it here for this. I can quickly go over again what I covered in today's lecture, but first I want to know if there's any questions or comments. Parts where you feel lost. Am I going too slowly? Am I going too quickly? Is it just right? Whatever. Good pace, okay? Okay, sure. We'll need to work on having people actually respond in the chat. But yeah, so we're starting with how to understand probability. Probability, in many ways, you already have an intuition for that's correct. In other ways, your intuition will fool you in sort of weird circumstances, but we'll talk about that later. In general, people have a pretty good gut level feeling of what probability is. We're going to be spending the first couple classes formalizing it. This isn't a probability class. You can read a probability textbook or take a probability class to have a more formal, proper treatment. But I'm going through the basics so far. And each of these things we'll be building on top of and referencing later. So it's important to try to wrap your head around these things and feel comfortable with them. And when you don't feel comfortable, ask questions. Even just saying, I'm totally lost, I have no idea what's happening, is a good comment or question to have, but you have to say it. Anyway, so we're defining a probability space. It's a set and a function, and we're kind of building the way that probability works. We talked about events, what it means for the probability of an event to happen, and that when you're talking about a sequence of events, that there's a formal, defined way of creating new probability spaces. In particular, a probability space is again made up of two things, a set and a function. The set is built by doing set multiplication. Go down here. So the set is defined doing set multiplication, and the probability function is defined by multiplying all different pairwise possible outcomes together in the individual worlds as the sequences are ordered. And that's it. So yeah, we're talking about how to formalize statements about probability and just to have the arena set up so that when you're thinking about things, they're all very concrete. None of this should be mysterious or confusing. If it is, ask questions. But the idea is to have everything be very clear and built on top of itself, and you understand the rules of the game. So that's it for today's class. Yeah, I guess I'll end a little bit early. I hope that's okay with people. It's like 10 minutes. The next thing I want to get into is going to take more than that, so I don't want to start halfway. I'll stick around for a few minutes if you guys have any questions or anything. Otherwise, you can email me. This is on the Blackboard, but this is my email. And I will post this lecture along with this OneNote presentation to Blackboard. Expect them up sometime this evening. Takes a little bit for the video to compile. So thank you, everybody. I'll stick around for a few minutes if anybody has any questions.